Heat a pure copper wire, and its ability to conduct electricity declines. Apply that same heat to a silicon wafer, and its conductivity rises dramatically. In metallic conductors, thermal energy impedes the flow of charge, increasing resistivity. In semiconductors, that same energy releases new carriers, driving resistivity down. This contradiction is resolved at the microscopic level through a single physical relationship. Resistivity, represented by the Greek letter rho, equals m divided by n times e squared times tau. The numerator, m, is the mass of an electron, and e is its elemental charge. Both of these are universal constants. They do not change, regardless of how much heat we apply to the material. The variable n stands for number density. This measures the amount of free charge carriers, the electrons, available to move per unit of volume within the material. The variable tau represents relaxation time. This is the average time an electron travels freely before crashing into the crystal lattice. Because n and tau sit in the denominator, they share a strict inverse relationship with overall resistivity. If the pool of moving electrons drops, or if their free travel time shrinks, the total resistivity of the material must climb. Every thermal effect measured on a macroscopic scale comes down to a battle between these two variables. Electrical performance is dictated entirely by how many electrons are moving and how many obstacles they hit along the way. Pure metals begin with a massive number density. They possess a vast ocean of free electrons at room temperature, and adding thermal energy to a metal does not significantly increase that number. The variable n remains largely static. When heat enters a copper lattice, the kinetic energy is absorbed by the atoms themselves. They vibrate violently in place. The free electrons attempting to flow through this space are forced to navigate a chaotic, shifting grid, causing them to constantly ricochet off the vibrating atoms. These frequent collisions severely cut down the distance an electron can travel freely before being deflected off course. This chart compares relaxation time with total resistivity. As temperature rises, our relaxation time tau steadily shrinks. Because tau is dropping while the electron count remains fixed, the overall resistivity curve is forced upward. This is known as the collision effect. It is the primary mechanical reason why metals become poorer conductors as their internal temperature climbs. This physical reality is consistent across almost all pure metallic conductors. Silver, copper, aluminum, they all suffer from the exact same thermal degradation. In metallic structures, thermal energy creates physical interference, increasing the frequency of collisions that impede the flow of charge. Circuit designers cannot measure individual electron collisions when engineering a system. Instead, they rely on macroscopic data that plots this collision effect into a measurable, predictable curve. This chart plots the thermal response of a typical metal like copper. Resistivity is tracked on the y-axis against absolute temperature on the x-axis. Over standard operating ranges above 0 degrees Celsius, this relationship is highly predictable. The line moves upward at a steady slope. This linearity only breaks down at extreme thermal lows. Approaching absolute zero, the data deviates, curving toward the y-axis. To model the predictable linear section of the curve, engineers use equation 3.26. Resistivity at a given temperature, ρT, equals ρ sub times the quantity, 1 plus alpha, times T minus T sub. Here, ρT is the new resistivity we are trying to calculate. We find it by starting with a known reference resistivity, ρ naught, which was measured at a baseline temperature, T naught. This equation provides a precise mathematical tool to calculate the exact thermal penalty a metallic component suffers as it heats up in the real world. The most critical variable in that entire equation is alpha.
This chart visualizes alpha, defined as the temperature coefficient of resistivity. The exact value of alpha directly dictates the steepness of the resistivity slope. For pure metals, alpha is universally a positive number. This mathematically encodes the physical reality that applying heat increases resistance. The dimension of alpha is inverse temperature. It explicitly measures the fractional increase in a material's resistivity for every single degree the temperature rises. Every metal possesses a unique alpha value. A material with a high coefficient is highly sensitive to thermal changes, while a material with a low coefficient maintains a much steadier resistance profile under heat. Alpha operates as a material's exact thermal fingerprint. It specifies precisely how much conductive efficiency will be lost for a given input of thermal energy. This linear loss of efficiency presents an immediate engineering problem.
Certain components, like standard wire-bound resistors or the heating elements in household appliances, must maintain a precise, unchanging resistance even as they generate enormous amounts of heat. Pure metals fail completely at this task. To solve it, we rely on metallic alloys, specifically blends like nichrome, which is a structural combination of nickel, iron, and chromium. This dual chart compares pure copper against nichrome. While the copper line slopes upward as heat is applied, the nichrome line remains almost entirely flat across the exact same temperature range. Nichrome behaves this way because its temperature coefficient, alpha, is exceptionally small. Its electrical resistance is nearly immune to thermal disruption. But there is a physical trade-off. Nichrome possesses a much higher baseline resistivity than copper right from the start. It is an inherently poor conductor, but it is highly stable under severe thermal stress. This specific stability is what allows a basic electric toaster to function. The nichrome heating element can glow at 800 degrees Celsius while continuously drawing a steady, predictable current from the power supply. By alloying metals, engineers trade raw conductive efficiency for thermal predictability. The material heavily restricts the flow of charge, but it does so reliably, independent of its operating temperature. While alloys merely mitigate the effects of heat, an entirely different class of materials inverses the metallic rule completely: insulators and semiconductors. In a pure semiconductor crystal like silicon, electrons are tightly bound to their individual atoms at room temperature. But as thermal energy enters the lattice, it provides the exact kinetic energy for electrons to break their bonds, flooding the material with free carriers. Returning to our microscopic formula, this means the variable n, the number density of free electrons, is no longer fixed. As the semiconductor heats up, n increases exponentially. The atoms in the silicon lattice are still vibrating, meaning the relaxation time, tau, is still shrinking. However, the sheer volume of newly liberated electrons overwhelms the penalty of those atomic collisions. If you place a copper wire and a silicon wafer under the exact same thermal stress, they react in opposite directions. The metal loses its ability to conduct, while the semiconductor is energized, surging with electrical current. This chart plots the inverse coefficient. For a semiconductor, mapping resistivity against temperature yields an exponential decay curve. As the heat climbs, the resistivity crashes towards zero. 3 different materials ultimately yield 3 completely distinct thermal trajectories. Pure copper degrades, nichrome holds steady, and pure silicon accelerates. These 3 trajectories are the macroscopic result of internal atomic structure. Metallic conductivity is defined by the limits of electron mobility, while semiconductors rely on the thermal density